All right, so not a lot to talk about in this second lecture on protein metabolism. We really are going to get into the details here of the metabolism of specific amino acids, of the alpha keto acid skeletons, how we dispose of nitrogen, so kind of getting into the urea cycle here. So this is kind of the last slide we ended with last time, and talking about some important chemistry that allows for any amino acid to ultimately either become glutamic acid via transamination with alpha ketoglutarate, or become aspartic acid via transamination chemistry with oxaloacetate. And herein we see another important purpose and use for vitamin B6, our pyridoxal phosphate, PLP. Once we have everything either as glutamic acid and aspartic acid, and again we'll talk about in a little bit what we do with these alpha keto acid skeletons, oxidative deamination chemistry is going to generate our ammonium ion, aspartate is going to provide a second nitrogen source, and bicarbonate will provide the carbonyl that we need to synthesize urea. So we're going to get into the nitty-gritty details of those biochemistries in today's lecture. I'm not going to spend a lot of time going over it in our overview here because we'll have time in our activities, but again, transamination chemistry, you kind of want to think about converting this alpha carbon nitrogen into a carbonyl. And in doing so, again, that allows us to swap out alpha ketoglutarate for glutamate, and then whatever was left from our original amino acid becomes a new alpha keto acid. Remember, alpha ketoglutarate is an alpha keto acid. Same thing with doing chemistry with oxaloacetate. And so we have these new alpha keto acids, and depending on who they look like will determine ultimately how they're metabolized. So we'll get into some of those details in our activity. But if you have funneled yourself to glutamic acid and become glutamate, oxidative deamination is going to be your fate. And so we're going to have glutamate here undergoing an oxidation here, so we've got reduction of NAD or NADP+, depending on the organism, generating this imine intermediate, and hydrolysis of this imine is going to liberate this free ammonium ion. So part of our activity is to look at the reaction mechanism for that, and we'll do that on the next slide here. But this is the critical part that we generate. We've oxidatively deaminated this, and we have one piece that we need for urea. Again, we're left with alpha ketoglutarate that can go back and continue those transamination reactions. So oxidative deamination of glutamate generates the necessary ammonium ion that we need for one piece of urea. So again, we'll go through the details of this in our activity, how oxidative deamination chemistry proceeds. We'll make sure that we remember how to hydrolyze something like an amine. And again, look at the urea cycle. So we are not going to go through a lot of details of the urea cycle, but we've got three main things that we need as recipe ingredients for urea. The ammonium is going to come from the oxidative deamination of glutamic acid. We've got our bicarbonate here, and then aspartate is going to provide the other nitrogen atom, and again that happens within the urea cycle. This is not a process without energy input, and the end product is urea, and then again fumarate, which hopefully we remember as a citric acid cycle intermediate. So nothing new on this slide, but again, a way just to summarize all the different pieces that we've talked about. We'll break this down a lot more in some questions in our activities. Now, your book spends a lot of time going through how you actually metabolize every single one of these alpha keto acid skeletons coming from different amino acids. So again, how you're metabolized depends on who you look like, but we can generally funnel things into two classes. And we've used these terms before when we've talked about the ability of certain amino acids to be converted into glucose. You're either a glucogenic amino acid or a ketogenic amino acid. Remember, glucogenic amino acids are those ones that are precursors to glucose. So they can be converted via gluconeogenesis into glucose if, for example, we're doing the Atkins diet. Ketogenic amino acids, on the other hand, are relatives of acetyl-CoA or ketone bodies like acetoacetate. And if you've kind of funneled yourself into that world, those are not substrates that can be converted into glucose. So again, only glucogenic amino acids from proteins can be converted into glucose. So I don't know, probably 14 or so pages in your textbook talks about the metabolism of all of these different amino acids. We're going to focus on two that have kind of interesting medical side stories, and that has to do with why pregnant women must take folate. So we're going to talk about the problem with high levels of homocysteine, which is called hyperhomocysteinuria, and why that can cause birth defects. But again, it has to do with the improper ability to metabolize an amino acid skeleton, specifically looking at methionine. And then we'll also talk about PKU. This is one of those metabolic disorders that they screen for. So again, if you're looking for a potential topic to think about with your presentation, look at some of those metabolic disorders that are screened for in infants. Those are really important ones, and kind of think about how they relate to concepts we've discussed in biochemistry. So again, phenylalanine is an important precursor for the synthesis of tyrosine, but phenylketonuria have no ability to metabolize phenylalanine because they cannot undergo this hydroxylation chemistry. So this can cause severe mental retardation within a few months if undetected, easily treated by avoiding phenylalanine in the diet. Now we say easily treated by avoiding phenylalanine. Avoiding phenylalanine in the diet is not necessarily that easy. So we'll spend a good bit of time talking about these two kind of medical case studies as a way to think about metabolism of amino acids. That's probably what we'll get through for this second lecture on protein metabolism.